Hello there. In this video, we're going to continue our discussion on how to measure the relationship between two numerical variables, and we're going to call them x and y. Let us consider the possible scenario that you study how many hours someone stays awake as a function of how many cups of coffee that they drink. Some people believe that these two variables may be connected to one another, hence that would motivate the whole entire study. So suppose you ask a bunch of people how many cups of coffee they drink, so 1 through 8, and also measure how many hours they stay awake. So as we see here, if you drink 1 cup of coffee, the person stayed awake for 14 hours, whereas the person who drank 8 cups of coffee stayed awake for 22.9 hours. So if you were to draw a scatter plot of this data, then you may see some type of trend between these points. So if this is x and this is y, then you may feel that there should be a positive correlation between these two values. So one thing you could say is this an increasing trend. Most people would say yes, of course. The more cups of coffee you drink, the more longer you would stay awake. So if you were to calculate some statistics on these things, then that should be also verifiable. So if you were to calculate the covariance between x and y for these particular rows, you're going to see that this is approximately equal to 6.61. And this is definitely greater than 0, so that would imply that there is a positive correlation between these values. You can also calculate the Pearson correlation coefficient R, and you're going to realize that that is equal to 0.95. So that implies what? So remember, covariance implies a positive trend. The Pearson correlation coefficient, this thing is positive, so this implies that this is a positive linear trend. And from the R, you would calculate probably the R squared value, and R squared is approximately equal to 0.90. And from here, you would say this is a strong, possibly strong, positive. Well, from this, you can't really say positive, but you can definitely say it's a linear trend. So from these three statistics, you can come up with the same exact observation as you would use just by looking at the data or understanding the problem itself. But making conclusions just from the variables x and y and what they measure would be a biased interpretation of the study. All right. So from here, what can we do? So clearly, we see that there is a linear trend between these variables x and y. Because we pretty much see that along here. So therefore, there should be some line that passes through these points the best. And I'm going to refer to this line as y hat. So to sort of distinguish between our y values and our approximation of our y values. All right, so this video is going to be focused on how to calculate what we call the line of best fit. Alright, so what is the line of best fit? So the line of best fit is going to have the structure y hat is equal to mx plus b, where m is the slope of our line of best fit and b is the vertical intercept. And again, y hat is going to represent the approximation to our y values. So what is m and b in this case? So the slope of the line of best fit, recall, the slope of a line is typically the change in y over the change in x. So if we were to take any y value, if we compare it to the mean of y, then that would be a pretty much general idea of the variables. But we would need to do that for all of the variables x and y so that this isn't a biased or a skewed estimate. So if you were to multiply top and bottom by x minus x bar, and you'll see why I want to do this in a second, and sum this up across all of the values, and of course you could divide top and bottom by m minus 1, then you pretty much get formulas that you should be familiar with. So if I rewrite this in a neater way, so this top is going to be the same as x minus x bar times y minus y bar, all over n minus 1. all divided by the sum of x minus x bar, the quantity squared, divided by n minus 1. And you'll pretty much see why I have multiplied and manipulated this standard equation, because this top equation is precisely equal to the covariance between x and y, and the denominator is precisely equal to just the variance of x. So therefore, the slope of the line of best fit is just equal to finding the covariance between your two variables and dividing by the variance of your independent variable. So this is the variance of your explanatory variable or independent variable. Alright, so since we know m, now all we need to find is b, right? So remember, y hat is equal to mx plus b. We already know what m is, so to solve this equation for b, we're going to say, okay, b is going to be equal to y hat minus mx. And typically what we usually do is we choose a particular point for x and y, we substitute them in, we do the math out, and then we find what b is. So what xy value are we going to choose to sort of substitute? So a good unbiased choice is, why not let x be x bar and y be y bar? So if you do that, then you're going to get the equation that the slope of the line of best fit is equal to y bar minus m times x bar. So this is the y-intercept of the line of best fit, whereas this is the slope of the line of best fit. And one can show, if you want to, one can show that these, in fact, minimize the total distance from a line to our data y values, which I'm not going to prove here. That is, there is no other line that is a better approximation than the line that has these two statistics to it. Alright, so let's go back to our example of the coffee and sleep scenario. So if we calculate the variance of our data value, and recall that's going to be the variance.s in Excel of our x values, that's going to come out to approximately equal to 6. So recall that the covariance between x and y was equal to 6.61. So if you know your variance of your independent variable and your covariance between your two variables, from here you can find the slope of the line of best fit to be equal to 6.61 divided by 6 approximately. And you're going to find that the slope of our line of best fit is 1.10. Alright, well that's great. So now we can find our y-intercept. So to find our y-intercept, we need to find the averages of x and y first. So x bar is going to come out to 4.5 and y bar is going to come out to approximately 19.51. So once you find those two and you've already found m, then your y-intercept is going to be equal to y bar minus m x bar, which is going to be equal to 19.51 minus m that we found up here multiplied by x bar. And remember to do your order of operations correctly if you're doing this manually. So that means b is going to be approximately equal to 14.56. So putting all this together in one clean statement, that means our line of best fit y hat is equal to 1.10x plus 14.56. So this is our line of best fit. So graphically, what does that give us? So recall we have our points scattered throughout this region, and then we have our line of best fit here. So this line here is this line of best fit. Now, is it going to pass through all of our points? Of course not, but the pretty much idea of what this equation does is this distance between all our blue points and this line is the smallest that you could be for any possible line that you could draw here. And that's for our variables x and y. And this, again, is what we call the line of best fit. Now, what can you use the line of best fit for? Well, you can use this for a couple things. For example, you can use this for extrapolation, is one example. So what does extrapolation mean? Well, if we have some data value here, suppose we want to find out, okay, how many hours will I stay awake if I drink, say, 4.6 cups of coffee? So plugging 4.6 into this equation is going to give us an approximation for that. Another value that we could sort of apply this to is forecasting. So forecasting is going to extend out of the domain of calculation. So let us assume that I drink 9 cups of coffee. How many hours will I stay awake? Well, again, you're going to plug that into the line of best fit and get some number out. And another method is what we call retrodiction, which pretty much goes before the line of best fit. So if I were to drink 0.5 cups of coffee, how many hours will I stay awake? You plug 0.5 into this equation, you'll get some number out again. But of course, if you're within the domain of calculation for the extrapolation case, this is actually going to be more reliable of a calculation than the other two, because these other two mandate that the trend still hold out of our domain of calculation. And we'll go into this a little bit more detail in a couple of later videos. But for right now, that's all I pretty much need to say about the general idea of the line of best fit, how to calculate it, and what it can be used for.